Let us begin with power spectral densities. We describe the random processes in both time domain as well as frequency domain. Autocorrelation, cross-correlation, covariation functions are used to describe and analyze the random processes in time domain. Power density spectrum, cross-power density spectrum are used to describe and analyze random processes in the frequency domain. Let us consider a random process x of t. We'll take a sample over the period minus t by 2 to plus t by 2, and that xt of t is the ensemble function of the random process x of t. And x of t is shown here and xt of t is shown here. It is defined for the period minus t by 2 to t by 2, and window length is t. And xt of t is defined as x of t for the period minus t by 2 to plus t by 2, and it is 0 otherwise. Let us apply the Fourier transform so that we can get the analysis as well as synthesis function to the windowed sample function. So we have xt of j omega. It is integral of xt of t with e to the power minus j omega t being integrated with respect to t over the period minus infinity to plus infinity. We can also get xt of t from xt of j omega using this equation 1 over 2 pi integral of xt of j omega e to the power j omega t integrating with respect to omega over the period minus infinity to plus infinity. The power of a signal is its power used and measured in terms of watts. Averaging the power of the signal x of t within a window of width t leads us the power function as 1 over t integral of x square of t dt over the period minus t by 2 to plus t by 2. Let us use the windowed sample function. So therefore, the average power is given by 1 over t integral of minus infinity to infinity xt whole square of t dt. So this can be written as xt into xt quantity xt. Uh, so that xt is written as 1 over 2 pi integral of xt of j omega e to the power j omega t d omega dt. Let us interchange the order of integration. So this 1 over 2 pi is a constant that has been removed out. So integral of minus infinity to infinity xt of j omega. This is minus infinity to infinity xt of t e to the power j omega t dt. So this is nothing but xt of minus j omega. So xt of j omega, xt of minus j omega being integrated with respect to omega, and this is divided by 2 pi t. If xt of t is a real function of time, then xt of minus j omega is equal to xt conjugate of j omega. So we can write the average power as equal to 1 over 2 pi t integral of minus infinity to infinity xt of j omega multiplied by xt of conjugate of j omega will give us modulus of xt of j omega whole square, this being integrated with respect to omega. Let us apply the Pascal's theorem. Using the Pascal's theorem, we can get t into pt is equal to integral of x square of t dt over the period minus t by 2 to t by 2 is equal to 1 over 2 pi integral of minus infinity to infinity modulus of xt of j omega whole square d omega. So we can write here that the integral of minus t by 2 to t by 2 x square of t dt is equal to 1 over 2 pi integral of minus infinity to infinity xt of j omega whole square d omega. Therefore, we can write the expected value of expectation of integral of x square of t dt over the period minus t by 2 to t by 2 is equal to 1 over 2 pi expectation of integral of minus infinity to infinity modulus of x of t j omega whole square We need to integrate this with respect to omega. So we can interchange the operation expectation with the integration. So I can write here minus t by 2 to t by 2 expectation of x square of t dt, that is equal to 1 over 2 pi integral of minus infinity to infinity expectation of xt of j omega whole square. We need to integrate this with respect to omega. Expectation of x square of t is a constant for a wide sense random process, as you are aware of it. The integral on the left can be evaluated as t into expectation of x square of t, because this is a constant. So when you integrate with respect to t, it becomes minus t by 2 to minus t by 3. That will give us plus t. So 1 over 2 pi integral of minus infinity to infinity expectation of xt of j omega whole square modulus. We need to integrate with respect to omega. Expectation of x square of t is given as autocorrelation function at t equal to 0. So rx of 0. So I can write this as t into rx of 0 is equal to 1 over 2 pi integral of minus infinity to infinity expectation of xt of j omega whole square. We need to integrate with respect to omega. As t tends to infinity, we get the average power in a random process. So Rx of 0 is equal to 1 over 2 pi integral of minus infinity to infinity limit t tending to infinity 1 over t expectation of xt of j omega whole square. We need to integrate with respect to omega. So this is will give us integral of minus infinity to infinity fx of omega d omega over 2 pi, where x's of omega x of omega is given by limit t tending to infinity 1 over t x, the expectation of xt of j omega whole square. Let us look into the properties of PSD, Power Spectral Density. First one is PSD is a real function of frequency. So the magnitude is real valued by definition, and expected value is therefore also real valued. Second one is the integral over minus pi to plus pi. The frequency range is proportional to the variance of a zero mean random process, and 2 pi is the proportionality coefficient. PST of a real value random process is an even function, which means that fx of minus omega is equal to fx of omega. PST can never be negative. That means fx of omega is always greater than or equal to 0 for all omega. So the Rx of tau is given by 1 over 2 pi integral of minus infinity to infinity fx of omega e to the power j omega tau, this product being integrated with respect to omega over the period minus infinity to infinity. So therefore we get fx of the omega is equal to the integral of product of Rx of tau e to the power minus j omega tau d tau. Rx of 0 when tau is equal to 0 is given by 1 over 2 pi integral of minus infinity to infinity. Since omega is equal to 0, tau is equal to 0, this becomes 1. So we have fx of omega being integrated with respect to omega. Let us consider an example. A power spectral density spectrum is as shown in the figure. For the random process x of t, the spectrum is assumed to be non-negative and it is real. It's an even function of omega. So we need to calculate the total power in x of t. So we need to find out Rx of 0, that is given by integral of minus infinity to infinity fx of omega d omega. We get this as 0.001114 as the answer. Expectation of x square of t is given by Rx of 0, that is as 1 over 2 pi integral of fx of omega with respect to omega. It is the sum of sigma x square plus mu x square. If the mean is 0, if mu x is 0, then Rx of 0 is equal to sigma x whole square. If mean is not 0, then Sx of omega includes an impulse of omega square s of omega at omega equal to 0. This is very very important. You should remember that Sx of omega if the mean is not 0, then it is going to include an impulse at omega equal to 0 and the magnitude is mu square s of omega. For example, we'll take first problem. Our PSD is shown in this figure where the constants are A is equal to 55, B is equal to 5, omega naught is equal to 1000 and omega 1 is equal to 100, which means that it varies from 900 to 1100. Calculate the values of each expectation of x square of t, sigma x square and modulus of the mean. Since it is an even function, so we will flip this and so we will be getting two spectrums here on the omega axis. Very important observation you can observe here, there is no impulse at omega equal to 0. If there is no impulse, it is understood that the mean value is equal to 0. Therefore, expectation of x square of t is equal to sigma x square. So Rx of 0 by 2 is given by 1 over 2 pi integral of minus pi by to pi Sx of omega d omega, that gives you 1 over 2 pi 2 omega 1 into b plus integral of omega naught minus omega 1 omega naught plus omega 1 a into delta of omega minus omega naught d omega. This we are considering as a triangle. So therefore we have two triangles here. One triangle has got this width is omega 1 and the height is b. So it is half of omega 1 into b and that has to be multiplied by 2 because we have two triangles here. So we get omega 1 into b and this we have 2 here. So therefore it has to be multiplied by 2. And here we have an impulse. So that impulse is being considered here. So mu x equal to 0. So therefore Rx of 0 we will get it as 176.66, that is equal to sigma x square. Thank you.